Hello and welcome back. So this video is over worksheet 18, which is our last worksheet. So this will be the last video that I post for the quarter. This worksheet covers three of what we call our outcome questions for the math department. And basically what that means is that we've got three questions here that include a lot of the different concepts that you guys learned over the quarter. And of course we put those, two of them actually, in an application type problem so that you're needing to use a lot of different skills and kind of put it all together. So I will kind of chart out maybe what units these come from if it's helpful to you. You guys can see in question number 1 we're dealing with exponents. So this particular problem comes from unit 11. So just in case you were not sure about a few of the things, you can actually go to unit 11 and do a little bit of reviewing. Okay, so problem number 1. Susan uses the following formula to calculate the cost of purchasing different numbers of bike tire pumps for her shop, where Y is equal to the number of pumps and P is equal to the cost in dollars. The question asks, how much does it cost Susan to buy 15 bike pumps? Okay, so we've got 15 bike pumps, which of course we know that bike pumps are Y. So we know that eventually here we want to make sure that we're plugging in 15 for Y to figure out what the total cost would be, because you notice here the cost is what we're looking for. All right, so I want to point out this hint right here. Please pay close attention to that. Whenever you guys can simplify inside of a parenthesis first before applying your exponent rules, you're going to save yourself a lot of time and energy. All right, so let's do that. Let's take a look here. For one, I want to notice that we have a negative exponent. Well, remember our negative exponents, any base to a negative exponent, let's call this a 2 just so we can have something different. So x to the negative 2 is the same as 1 over x squared. So basically, if we can think about this as the original, we'll make it a fraction, we'll just put it over 1. We're just flipping that over and we're changing that exponent to a positive. If we happen to have a over b to a negative exponent, let's just call this m, negative m, we can actually fix that negative exponent by flipping the fraction. Basically, we're moving the b upstairs and the a downstairs, right? And that is the idea. We move whatever it is, wherever it is, up here. We notice here, this is in our numerator. Well, if we move it to our denominator, it fixes that negative exponent problem. So we can do the same when we have a fraction. We just flip it over and then our exponent becomes positive. So let's apply that knowledge to this problem. So we have this 3y to the 7th over 75y to the 8th to the negative 1. So let's just flip this over. 75y to the 8th over 3y to the 7th. So we have flipped that fraction over, which then helps our exponent then to become a positive instead of a negative. And we also know that when we have anything to the power of 1, it just is the base itself. So we can end up dropping this exponent in the end, which is helpful. So now we just need to pay attention to what's inside the parenthesis. Let's look at the number part. This is kind of like a fraction. We know that 3 goes into 75 25 times if we just think about quarters. And we can either use the quotient rule here on our y's, or we can consider the fact that we have 7 y's on the bottom, which is going to take 7 away from here, leaving just 1. Right? If you're using the quotient rule, you would just say y to the 8 minus 7, which is y to the 1. And once again, we know that anything to the power of 1 is just the base itself. So we can rewrite this whole entire expression here as 25 y, because we can drop that 1. And we notice on the bottom there's nothing left except 1s, right? But so we don't even need to write that. I mean, we could do that, but we don't need to do that, and so we just leave that as a non-fraction there. And since that's to the first power up here, like I said, we can just drop that right off. So we have the total cost, P, is equal to 25y. Way, way, way simpler than having to deal with all of the exponents and the negative exponents and all of that. All right, so we're going to come back up here to what our task was. We know that we need the total cost P when y is 15, when the bike pumps are 15. So we're basically going to be coming back up here, and every time we see a y, which is once, I'm going to put in a 15. Whoopsie. 25. So now I have my expression just in terms of P. I don't have anything else in there, and we just need to do the math. So 25 times 15, that gives us 375, and we need to think about our units. Remember that P is cost in dollars, so we're just going to add our dollar sign there. Okay. So basically, if we were to write out our answer here, we can just say it will cost $375 for 15 bike pumps. Okay guys, so you can see that this problem is not that difficult when you think about simplifying inside first. Please do that. You will see a problem like this coming up. All right, problem number 2. A patio that extends from a house is in the shape of a right triangle. One side is 4 feet longer than the shortest side. The hypotenuse is 8 feet longer than the shortest leg. Okay, so you guys can actually remember, I'm assuming you remember in Unit 11 that you had problems like this. I think it was on worksheet number 11. No, actually that would have been Unit 12. That was worksheet number 11 was in Unit 12. So this starts out with this idea of polynomials in Unit 11, but we also extend that into Unit 12 because we're going to be doing some expanding some binomials, and then we're going to be factoring and solving. All right, so this patio is in the shape of a right triangle. In A, it asks us to make a sketch of the triangular patio and label the lengths of all 3 sides using the information above. All right, so let's do that. Let's start out with sketching a right triangle. And this is kind of like our step number 2, 1 or 2, depending on which problem-solving steps we're using. But this is where we're really getting into defining our unknowns. Okay, and of course we need to do that. We need to define our unknowns, meaning we need to pick variables that stand for different things so that we can plug those into the equation and solve for what we're looking for. So we always know that when we have multiple unknowns, we start with the one unknown that we know nothing about. All right, so here we go. Let's take a look at some of this information here. We have one side is 4 feet longer than the shortest side. Okay, so for right now, we don't know anything about the shortest side. Right now, the shortest side is what I don't know anything about because I do know something about this one side that it's talking about. And then it says the hypotenuse is 8 feet longer than the shortest side. Once again, I know nothing about the shortest side. So this is going to be where I'm going to start. So my shortest side, we know that in a right triangle, both of the shorter legs are A and B, right? It doesn't matter where we label those. We definitely need to be careful and label the longest leg as the hypotenuse. That's the only side that we need to be super careful about. All right, so now we know that the hypotenuse, I'll jump down here, the hypotenuse is 8 feet longer than X. Okay, so here's my short side and the hypotenuse is 8 feet longer than that. Okay. Now, anytime you guys have a binomial or a polynomial as a side length or something that you're working on in a problem, go ahead and put parentheses around it. Okay, because we know that that dimension is x plus 8. It has to stay together. We're not separating that. Okay, now let's go over here to the one side. One side is 4 feet longer than the short side. So this is 4 feet longer than x. So this is going to give us x plus 4. And once again, we're going to put the parentheses around that. All right, moving on. Okay, B, use the Pythagorean theorem to write a quadratic equation that shows the relationship among the three sides of the triangle. Well, we know Pythagorean theorem is a squared plus b squared equals c squared. That helps us to find a missing side length, doesn't it? Well, in this particular case, we haven't really defined our sides as a, b, and c, but we could easily do that. We could say a is our x, b is our x plus 4, and of course c is our x plus 8. C is definitely the one we have to be careful of. All right, so let's just go ahead and input our x's instead of our a's, b's, and c's. X plus 4 squared is equal to x plus 8 squared. All right. Now in C, we're supposed to solve the quadratic equation and determine the length of all three sides of the triangle. So here's some important wording. Solving a quadratic equation, we need to remember what that is, right? And we know that that is going to involve factoring, right? When we solve a quadratic, we have to factor it first, and then we set each factor equal to 0. And in the end, we are determining the lengths of all three sides of the triangle. That's our unknown. That's kind of our goal. All right. So let's go ahead and bring down our quadratic equation here, or our Pythagorean theorem that we have converted to a quadratic equation, because we will see it appear here in a moment. All right, so let's go ahead and do some math here. This x squared is going to stay x squared, but we have to be careful here. We know that x plus 4 squared, the quantity squared, means that we have two binomials that we are multiplying together. The base is x plus 4, so we have two of them. So in this case, we're going to FOIL. Remember that it is not just taking this 2 and saying, oh, that's just x squared plus 16. We know that that's not true. That's a very common error that happens in these types of problems. So just be really careful about that. And then this is going to equal the same sort of scenario. We've got 2x plus 8 that we are multiplying together because x plus 8 is our base. And we know that the method that we use to do that would be the FOILing method, right? So we're going to take that x and multiply it by both terms in the second parenthesis. Let's do that. So I'm going to have x squared plus 4x. And then we'll take that 4 and multiply it by both of those terms. Okay, so that's that FOILing. I'm going to just bring this straight down and kind of show what we're doing here that way. And we have another FOILing to do here with these two binomials. So we've got x squared plus 8x. And we're going to do the same thing with our 8. All right, and then we can see that we have some combining like terms that we can do here. I'm going to just go back to the black here. All right, so I've got x squared plus x squared. In fact, what I can do, I was not going to because we would see something actually happen if I didn't combine them, but I'm going to go ahead and combine them. So 2x squared plus 8x plus 16 is equal to x squared plus 16x plus 64. All right, now one of the things you guys might have seen up here is that if we have x squared on the same side, or excuse me, x squared on different sides of the equal sign and they're the same sign, we can just cross them out, right? I decided not to do that because I'm going to go ahead and just solve this in a little bit more traditional manner, but if you guys saw that, you could have done that. You guys can see that these are quadratic equations, right? They're in the form of ax squared plus bx plus c, and we have it on both sides. So anytime that we're asked to solve a quadratic equation, we know that we need to factor, well, actually we need to set it in standard form, right? Set in standard form, and remember that our standard form of a quadratic equation is ax squared plus bx plus c is equal to 0. Okay, so somehow we need to get all of the terms on the right over to the left, and the reason I want to do that is you notice I've got the 2x squareds on the left and just 1 on the right. So I'm going to bring everything over. Basically, I'm just going to subtract all of these because they're all added. If I do that, you can see these are all going to go away, leaving a 0, right? So this is what I want. You can look up here at the standard form. And we have to, of course, do the same here. Minus 16x minus 64. No problem. We'll just do that math there. Okay, so it looks like we are left with x squared minus 8x. And then we have a 16 minus 64. That's going to give us a negative 48 is equal to 0. I'll move this down a little bit. All right, so we have it in standard form. It's set equal to 0. Okay. Secondly, we in order to be able to solve the quadratic equation, we need to factor it first. Well, luckily a is equal to 1. Let's go ahead and show what our a, b, and c are. Here's our a. Negative 8 is our b. And negative 4 is equal to our c. So we can just set up our t-table. We know that a times c is going to equal negative 48. Okay, so we need factors of negative 48 that add to our middle term, which is negative 8. So I have a negative product and a negative sum. Well, the only way for me to get a negative product is going to be a positive and a negative. Okay, so I'm going to be thinking of factors that are positive and negative, and that would give me a negative 8. So I'm thinking negative 12 times 4. I know that that's going to give me, when I multiply that together, is negative 48, and a negative 12 plus 4 is going to give me a negative 8 as sum. So that is what I'm looking for. So I'm just going to bring these over here. This is going to give me an x minus 12 times an x plus 4 equals 0. So here's the part that sometimes students forget. They kind of just stop after they're done factoring. But remember that we are asked to solve this baby. So in order to do that, we need to set each factor equal to 0 and solve. Okay, I'm kind of out of room here, so I'm going to move this direction. So let me just make a bit of room here. All right, so we are going to have x minus 12 equal to 0, or x plus 4 is equal to 0. Well, if we add 12 to both sides, we can see that x is equal to 12, or x is going to equal negative 4. And in these application problems, most of the time, you're going to have to make a choice. One of these is going to be appropriate and one is not going to be applicable. And we know that there's no way we're going to have a negative side link to a triangle, so we're going to choose the positive option. All right, so x is equal to 12. So we can kind of go back up here to our sketch, right? So we can show that x, we know that x was our short side. Sure. So our short side is equal to 12, and we need those units in there. So we go back and remind ourselves. That's feet. So I can't talk here. The short side is 12 feet. The other side, remember that the other side, we just added 4 to that. Here's our other side up here, right? We just added 4. So we're going to get 16 feet for that. And our hypotenuse, we actually added 8 to x. So that's going to be our 20 feet. Now, we know in these application problems that we always want to do a check as well. And that's very helpful because it really tells us whether we did the right thing. We can easily plug this into the Pythagorean theorem and just make sure that it works. That helps us to know we did the right thing. So we're going to say 12 squared plus 16 squared needs to equal 20 squared. So 12 squared is 144. 16 squared is 256. 20 squared is just the same as 2 squared, which is 4. And then, of course, we're going to double those zeros, too. And 256 plus 144 is indeed 400. So we are happy campers. All right, guys, so that's what that would look like. You can see there's lots of steps, but it's very systematic, and you can see that the unit 12 comes in down here in the C part of question number 2. All right, let's move on to the last question here. And question number 3 is all about unit 13. In fact, I know that you had a question on one of your worksheets. I also did a video on this one. I believe, if I'm just thinking on the top of my head, I think it's worksheet 13. And it was a problem very, very similar to this. Okay, so when you're attacking these application problems, a good idea would be to a couple things that they don't really say on the actual problem generally is to read through the whole problem first, just to kind of see what you're getting into. The other thing is I would always recommend to just start a t-table of values. That's going to help for so many reasons. You're going to need a lot of those values. You're going to be pulling values out from the original problem itself. You're going to have to scale and figure out dimensions on your graph. Well, the t-table helps with that. So those would be 2 things that I would always recommend that you do. Also, one comment is that in these types of problems, guys, when you know that you're going to be working on an application problem where you have to come up with an equation, in this particular case, we're talking about a linear equation, and we're going to have to be graphing that. I want you guys to think about what are some of the scenarios that you have encountered that will help you to write an equation. So remember, when we're writing an equation, we're given either a graph, so we can come up with our m and our b, because this is also an important thing to remember, that when we're dealing with linear equations, if we choose to use the standard form here, this is the slope-intercept form, which is what we've been actually using this whole quarter. You have just basically 2 objectives. You need to find your m and you need to find your b. Once you find your m and your b, you are good to go. And if you're given a graph, you can find those on the graph. The second scenario would be you have an application problem that they give you the slope and they give you 1 point so that you can solve for b. You can plug, the x and the y in to your equation right there, and you can solve for b because you'll already know your m, so of course your m will be inserted as well. The third scenario will be they're not going to give you any of those things. They're just going to give you 2 points. And we know that we can easily find our m from 2 points because we also know that m is equal to the difference between your y points over the difference between your x points, right? That's how we can find our m. And if they give you 2 points, of course you can plug one of them back in, like we were talking about here, and solve for b. So as long as you remember that that's your job, is to find m and find b, and once you find those, you're good to go, then you can kind of start searching for what information they give you in the problem. So let's do just that. All right, volunteering. The number of volunteers from the millennial generation, those born between about 1982 and 1999, has increased from 6.1 million in 2003 to 11.6 million in 2010. So if you kind of think through the scenarios that we just talked about, you notice obviously we don't have a graph, and they didn't give us a slope, but they did give us some information here that we can create 2 points out of. Now, I wouldn't do that just yet. Like I had said earlier, it's a great idea to read through your problem. Okay, A, what is the rate of growth based on the information given? Hint, this is your slope. Slope can be represented as a decimal number rounded to the hundredths place. So rate means slope. Okay, anytime you hear that in a problem, rate of change, rate of growth, that is going to be your slope. And they're telling you that it's okay to have a decimal if you know, and you often will. You're not going to have some nice, integer or a nice fraction like 3/4 generally. You're going to have some decimals in there. You go ahead and get on your calculator and figure it out. And if you can round to the hundredths place, that's just fine. B is asking us to find an equation for the line that contains the given points. It also helps us with our defining our variables here. It's asking us to let x represent the number of years after 2000. Okay, that's important, that word after 2000. And then y is going to be the number of volunteers in millions. And then down below in C, they're asking us to graph the number of volunteers from 2000 to 2010. They want to make sure we scale our graph, and we need to include all of our labels and label our points and all of that. And then down here in D, we're estimating the number of volunteers from the millennial generation in 2008 and 2014. Check your solutions using algebra. Now, for those of you who kind of like to do the estimating, you can wait till the end. That's fine. You're going to just look at your graph and you're going to estimate. If we remember here that we're estimating the number of volunteers, if we go up here, we can see that volunteers, let me just use our blue because we can see in B that Y is the number of volunteers, right? So we're going to estimate that number when our years are 2008 and 2014. The other option that you can do is you can include those in your t-table ahead of time so that you already have the math of it, right? You already have the exact number, and then you can look at your graph and see that your graph kind of correlates with that. All right, so let's go back up to the beginning here. So let's actually pull out our points. I think that's a really good idea to start with. If we know that x needs to represent the number of years after 2000, let's come up with our point here. So 2003. 2003 is 3 years after 2000. So we're not going to put 2003 down as our x. We're just going to put 3. 3 years after 2000. 6.1. And in 2010, we would have a point of 10. 11.6. So there is our two points that we can deal with. And of course we know, we talked about this before, our job now in order to be able to write an equation is to find our m and find our b. And you can see that in A it's asking us to find our m, right? So we know with 2 points we can use our handy dandy formula here. And remember, guys, it does not matter whether we call this one our first point, which I will do, y1, x2, y2, it doesn't matter. I could have reversed those. It doesn't matter at all. As long as you're keeping the y's on top and the x's on the bottom, and as long as you, for example, if I start with this y, I have to start with this x as well. You can't flip those around, otherwise you're not going to get the right numbers. So I've got 11.6 minus 6.1 for my y's, my change in my y's, and I've got 10 minus 3. So 11.6 minus 6.1 is going to give me 5.5. And I know that 10 minus 3, of course, is 7. Now, we would never want to use this as our slope. We have a decimal in the numerator, and that's just ugly. So if we just take our calculator and take 5.5 divided by 7, and we round that to the hundredths, we're going to get a slope of 0.79. Okay, so that works a lot better than 5.5 over 7. All right, now our job is to find the equation of the line. Okay, so of course we know we also have to find b. We know m, but we have to find b. Okay, how do we do that? We plug one of the given points. It doesn't matter which point you choose because both of these points should be on our line, right? Both of those should work. So I usually try to pick the one that is the least amount of work in terms of algebra. So some easier numbers or smaller numbers, something like that. All right, so I'm going to have, actually I'll go back to black here first. So of course I'm going to have my y is equal to, I'm going to plug my 0.79 in because I know that's my slope, x plus b. And then in order for me to solve for b, I have to replace my y and my x as well, don't I? So I'm going to replace that with the first point, which is 6.1 for y, 3 for my x, just plugging those in. 7.9 times 3 plus b, and now b is my only variable, so I'll be able to solve for that. 6.1 is equal to 0.79 times 3. It's going to give me 2.37. And if I subtract 2.37 from both sides, that's going to give me 3.73 for B. And since it's asking me to find the equation, we can't forget that we have to put it into an equation form. So we're going to have y is equal to 0.79 x plus 3.73. So this is our equation that's going to represent the information that we have so far about the volunteers and the number of years after 2000. All right, so I know we talked about this already, but in order for us to create a graph, create the points that we need for the graph, we want to set up our t-table. Right, so let's do that. So we got an x and our y. I always like to start with my intercepts. That's kind of important, and we can find our intercept right from our equation, right? When x is 0, it's going to wipe out that 0.79, and we know that b is our y-intercept anyway, so we can just look right there as long as it's in the correct form, standard form. I can also put my 2 points in. I know that when, where's my points here? When x was 3, so in 2003, there were 6.1 volunteers. I'm going to make room for 8 because I know down from D, I'm going to need to know the number of volunteers when x is 8. I'm also going to need to know the number of volunteers when x is 14. So I'm going to put an 8 in here, do some math here in a minute. From my original problem, I know in 2010, there were 11.6 million volunteers. And then I also know I'm going to look for 14. So this is going to give me lots of good points to put on my graph. So let's do some math. We want to know what happens when x is 8. So basically what we're saying is we can use, you guys are going to see this when you're in Math 99, f of 8. This is just saying, okay, when y is 8. That's all that really means. 0.79. And see, I'm going to not do that because let's throw something in that we don't actually really need. It's okay. So let's just do when it's 8. So y is equal to 0.79 times 8 plus 3.73. And if we do that math, I did it ahead of time, so I really can't do mental math that fast, I promise you. 10.05. And I'm happy about that because we can see that that fits really nicely between 6.1 and 11.6. So it means it probably did, whoopsie, did the math correct there. All right, we're going to check out 14. So what is y when x is 14? And when I did that math, we get 14.79. All right, so we have this whole set of values that we can put onto our graph, and I need to make room, so I'm going to have to get rid of this now. All right, so here's why our, all right, let me do this. Goodness, why is this not letting me do that? There we go. Here's why our graphing, our t-table is really important here. So we have a 15 by 15 grid here. I need to start looking at my dimensions, and what that's going to be is just kind of looking at the high and the low of my x. So you can see that the low is 0, the high is 14. The question also asks me to graph the number of volunteers from the years 2000 to 2010. I might as well go all the way up to 2014 since I know down here I'm going to need to have that information, right? So what that means is that I can come to my graph, or to the graph here, and I can start here at 0, and you don't have to list every single number if you don't want, but I have plenty of room to go by ones. So I'm going to 1, 2, 3, 4. This is going to be 5, 6, 7, 8, 9, 10, and 15 is over here. I have to clean this up here. I also want to make sure that I'm labeling the axis correctly. So this is going to be years. And I want to make sure that I know that this is years since 2000. Okay, so this is going to go from 2000 to 2015, basically. All right, now let's take a look at our y-axis. We can see that our low here is 3.73 and our high is almost 15. So that's another kind of similar situation. You notice that we could go down to 0, which would be right in front of the 3, and 14.79 is almost 15. So I think that we would be okay to go by ones there as well. If it went like 3.73 to maybe 5 point something, we would want to go less than 1 on our scale, because we would want to be able to graph those kind of awkward decimals a lot easier. The smaller the number on your scale, the easier it is to see, the changes, the intervals on your graph. All right, but I think we're safe to just do the same as our x-axis. So, oops, what the heck? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 15. We also know that this y-axis represents the number of volunteers. And we always put our units This is in millions. And I'm glad that it's in millions because we don't want to write all those zeros, right? That would be a pain in the butt for us to do that. So here's our y, here's our x. Okay guys, so then we're just going to start plotting our points. So 0 and 3.73 is going to be somewhere around here. I'm going to label them after I plot them, so I don't know where I'm going to need to plot the next one. All right, so 1, 2, 3, so this is when in 2003, we've got 6.1, so that's going to be just above the 6 there, 6 million. Okay, here's my 8 and 10.05, so that's going to be just literally almost right on there, right on the 10 basically. And then we have 10, 11.6, so that's just about halfway between 10 and 11. No, it's not. Just like, that doesn't look right. What the heck is wrong? It's not correct. 11.6. There we go. About there. Now that looks better. If that ever happens and you see that your points are not in line, go back and check it like I just did, because I knew something was up with that. Okay, and here's my 14. And we're going to go almost all the way up to 15. Now, when you do that, of course, your points should be in a nice straight line. This is supposed to be a linear function, right? A linear equation. All right, and then of course we would go back and label our points. 3, 6.1, 8, 10.05, 10, 11.6, and lastly 14 and 14.79. All right, so we already have the math from below. Okay, so we can go back, we can answer that question if we want to. In 2008, we found out that there were about 10 million volunteers. And let's check this out. Let's check it out, make sure that that was about right, 2008. I mean, obviously, if we didn't know that and we had followed this up, we would have seen right there, we would have probably guessed or estimated about 10 million, right? It's hard to guess a 0.05, but we would have taken a pretty close guess there, and it also proves that our graph is good. 2014, we decided that there were 14.79 million volunteers. I better put that in here, millions. In millions. And of course we can check that one out too. And 14 can go up. We know we graphed it correctly, right? This is gonna be just below that 15. So our graph is good. Everything seems to be kosher here. All right, guys, so that's it. I know that there are a lot of steps, but you're kind of putting it all together. You know, everything that you kind of learned in that unit in 13, kind of putting it all together. So practice this. We have similar questions on the final review as well. Okay, there are 3 questions that are just like this. And hopefully we'll see you at the Zoom Q&A. All right, guys, we'll talk to you soon.